Hello, my name's Ryan, and today I want to talk about the Polymorph entity component system for Nim. So what's an entity component system? Well, it's basically just an architectural pattern for runtime composition, and it consists of three elements. We've got entities, which are abstract identifiers, essentially the same as an abstract object in object-oriented design. We've got components that are just plain data types that you can attach to entities. And we've got systems, which is any logic that uses components for parameters. So why might you want to do this? Well, the first reason is that it's data driven. So behavior isn't fixed at compile time, but composed with parameters, otherwise known as components. And this gives you a lot of design agility. It becomes much more easier to pivot entire designs as everything's completely decoupled and systems are isolated in the data that they process. And also you get inversion of control. So there's no need to worry about the boilerplate of when something needs to be run. It just runs when the data is present. You don't have to worry about it. And finally, you get high performance pretty much for free. So the data-orientated design of an ECS lets us take advantage of pipelines and caches and other CPU goodies like that without you specifically having to declare it. So in a nutshell, what are we actually doing when we're writing software with an ECS? Basically, we're just creating composable logic and then stacking the parameters for that logic together, and this gives you the behavior that you want. So I'd like to talk a little bit about how ECS compares with object-oriented design, because most developers are more familiar with that. And object-oriented design tends to describe is-a relationships, and this is the primary difference between object-oriented design and ECS. So an object in OOD is a particular thing, and its subclass is a particular thing. It's a defined relationship. And this lets us define things from a top-down perspective, going from the concept of a particular job or task down to the nitty-gritty details and mechanics of how it's put together. ECS, by contrast, goes the other way. It defines has-a relationships, and this is bottom-up. So you can describe the mechanics of the processes involved, and then compose them into the concepts that you want to create. So here's a simple example of what you might do with an object-oriented design. So for example, with a game object, you might have the data for position, velocity, gravity, and so on. And then you might override the particular processes involved with different ones according to your needs. And this is good enough for most situations, but when you have a very complex project, you can end up with things that are basically like God objects. So they've got so much functionality, they're not really a defined concept themselves, because you have to fit everything into them, and it also becomes much more difficult further down the line when you need to have things that you didn't originally plan for, because the structure of the objects actually inhibits you. And then you have to refactor things, and that can get really expensive. So by contrast, ECS splits out data and systems, system logic. So basically, you take out the data parameters that you have, so position, velocity, gravity, and so on from our previous example. And then you just create logic that uses those directly. They're completely decoupled. There's no relationship between them. Movement only cares about the position data and only cares about the velocity data. For example, if you want to change how rendering works, you don't have to affect any of the other systems at all, because they're completely isolated. So here's an example of how this looks when you start stacking things together. So you can see that the white boxes are representation of an entity, and each entity will contain different component parameters, and you can see in grey the systems that those invoke. So already we've got inherently more concepts that can be built from these component parts than having to plan ahead into one tree structure of how it's all organized. You can see here we've got scenery, which is just position and render data, whereas when we add velocity, then things move, and gravity, then things fall from the sky, and so on. So we can actually build up things like players and flying enemies and so on by just defining the data separately. And this is quite nice because you can do all this at runtime. So for example, if you remove the render component, then something's invisible. If you remove velocity, then it becomes stationary. So this actually gives you quite a bit of functionality on its own, and allows you to prototype things at runtime in many cases, which saves a lot of effort and also makes things a lot more flexible. All right, so let's have a look at some code and see the library in action. So for this example, we're going to build a simple physics simulation. And the first thing we need is some component data to process. So after importing the library, we use the register macro to pass some type definitions, and they'll become our components. So here we're producing 4 components: position, velocity, gravity, and bounce. And you might notice that the first 3 components have data fields, but bounce doesn't have any data. That's because we're going to use this as like a tag component so that it triggers a certain system when it's added to an entity. So here's what the move system looks like. First, we need to give it a name, and then we just tell it which components we want it to use. And then we're going to use the all block to process every entity that has these components. And we're just going to add velocity to position. Similarly with gravity, we're just going to reduce the y component of velocity by the gravity strength. And finally for bounce, we're just going to make sure that position doesn't go below 0 in the y component. And if it does, we're going to make sure that velocity is positive and also halves its magnitude so that we get that kind of bounce effect. So after we've done that, we need to actually build the ECS framework, and this generates the actual code so we can use entities. And we use make ECS commit to do this, and we pass it the name of the run procedure that executes all the participating systems. So here's what this looks like when you're creating entities. So first we're going to create a moving entity that uses position and velocity so that the move system is triggered. And then if we run the systems once, only move is actually involved here. And finally, echoing the entity, we can see that position has in fact been incremented by the value of velocity. And it also tells us that this entity is part of the move system. So next we're going to add gravity. And when we do this, we can see that the entity is now part of the gravity system. So let's run this and see what happens. Before we do that, we're going to fetch the position and velocity components. And when we do this, you get an instance, which is kind of like a reference, but it's not garbage collected. It's basically an index into the storage. So it's nice and quick to use, but there's lots of sugar to make it act like it's a kind of original object. And then we're going to run all of the participating systems a few times and display the results of position and velocity as we do so. And you can see here that the y component of position goes up and then gradually goes down as gravity increases. And now it's gone below 0, but we don't want that to happen. So we're going to add the bounce component. When we do that and echo the entity, we can actually see that it's now part of the bounce system as well. So let's see how this looks when we run it. So here you can see that as x continues in a linear way, y gradually goes up and then hits a peak and gradually goes down again. But when it hits 0, it starts to ascend and then go down, and eventually it will settle at 0. So having given a quick demo of what that looks like, Polymorph also comes with a companion library called Polymers, which includes a lot of plug and play components that you can just use straight away to achieve particular effects. So this covers things like OpenGL instance rendering, database querying, spatial mapping for things like collision detection, and also networking components like TCP, HTTP, and RPC. And these build on each other, so you've got that kind of hierarchy there of how these components interact. And finally, there's also a console output for Windows that lets you draw characters as if they're in normalized OpenGL coordinates, -1 to 1, that kind of thing. So here's a demo from the Polymorph library showing the particle effects in action, and this is just a million entities being rendered so that they interact with the mouse. This is just a brute force interaction. It doesn't do any special spatial mapping or anything like that. So as you move the mouse about, all of the entities in here will just check the mouse position and respond. But we're still getting pretty good performance for this. This is only about 250 lines of code. So you can look at how this works on the demos folder in Polymorph. And as we can actually turn on a system that converts the colors to display the velocity, which you saw in purple there. The nice thing about ECS in general is you can just turn on and off systems in order to control processing without affecting anything else. So another example from Polymorph is a basic game. So this has most of the components you need for simple games. You've got collision detection, area of effect damage, damage over time, font rendering, levels, death, that kind of thing. And you can see here, once you've killed all the enemies, it goes on to a new level, and gradually the enemies get more health, they start doing seeking bullets and things like that. Okay, so what makes Polymorph different from other ECS implementations? So the first one is that it's queryless, which we're going to talk about next. And the second is that it's completely generated from your component and system design, which offers a lot of advantages, both in terms of performance, but also code size and scalability. And there's also a lot of static safety for things like use after free when you're iterating in systems and events that cause recursion and stuff like that. And the library is also agnostic for what you use it for. So ECS was originated in the game development industry, but Polymorph doesn't make any assumptions that's what you're going to use it for. There's nothing built in for game dev. So this means you can use it for whatever you want. You don't have to worry about other stuff you're not going to use. So one of the main things that an ECS has to worry about is feeding systems component data. And there's a few approaches on how to do this. A common approach is to use a querying solution. So usually you have a component or entity orientated data model. And this means that systems query a central manager, like a database of component or entity data, and work from that. And this is optimized for the common case at runtime based on the current data that's in the central manager and so on. But there's a few issues with that, because there's a mismatch between system execution and actually getting the data in the first place. So there's an overhead to beginning the query and actually fetching the data in order to start processing. There might be an overhead for filtering gaps in memory for dead entities and so on, or for clustered archetype ECSs. You end up having to move the memory about when you change components, which can be quite expensive. And you can get fragmentation there where you've got lots of different types of archetypes. And generally this just adds a lot of runtime complexity. You've got to have the code for the manager. You've got to make sure that everything's organized for performance, and this adds a lot of size to the code and overhead, call stacks, that kind of thing. So Polymorph implements a queryless solution for ECS, and this is orientated around systems for the data storage. So it acts like a system state machine, essentially, where systems are lists of components and you incrementally update them when you add or remove components to entities. So this has some quite nice characteristics. One of the main ones being that there's absolutely zero execution overhead for systems. So they're not doing anything at all to process data. They just work through their lists, and if you want to run them again, they just carry on again. There's absolutely no work there. There's also quite a low cost of changing components because you're just updating system lists. So that's nice and quick. And component changes can actually be pre-baked with metaprogramming so that the systems that need to be updated can be determined from the static types that you're using when you're making component operations like adding or removing components and so on. And this means that the output is optimized to specific designs at compile time, which can make it quite scalable if you have resource constrained environments, or if you just want to use as much memory as possible, then that's equally possible. So here's an example of static safety checking. This system removes bounce, which immediately invalidates the current row because it has to remove the entity from the system because it no longer matches, which is fine. Polymorph allows this completely. There's no worries about that. But if you then try and access bounce afterwards, you get this error, potentially unsafe access of item due to a removal of components that affects the system. And then it gives you a line trace to the echo above. Okay, so let's have a look at some of the code generation output that's produced by using the ECS. And Polymorph automates the generation of component storage, system types and procedures, state changes, so this is things like adding or removing components, and construction and delete procs that have some sort of dynamic element and need to know all of the components of systems before they are made. So here's the gravity system from earlier, and if we look at what this actually outputs, it's literally just a while loop. So that, you know, that this is great for optimization for compilers. It's really light on the instruction cache, incredibly short call stack for debugging sanity, and just simple code for both in terms of size and actually processing. For new entities, because we already know what systems use what components of things, we can actually pre-optimize this, and so the output becomes something like this. So we're just literally creating a new entity slot, adding the position to the slot for position storage, and updating the entity metadata, and it returns to you. So that's incredibly fast. But what if we actually need to update a system? So here, for example, we're adding position and velocity, and we know that this affects the move system. And then the output gets changed slightly because it just adds a link to update the move system. So there's no speculation involved because we know that the entity is empty beforehand. And we can just directly update the system because we know that that's what's needed and nothing else. With things like add and remove, however, we do have to speculate on the system, on the entity rather. So this becomes a little loop through the entity metadata to pull out, in this case, velocity, and make sure that if this is there, then we'll also update the gravity system. But if not, we'll just update the entity metadata, and that's the end of it. For more complex systems that need more speculation, this loop through the metadata is actually pared down, so it's always one pass and will short circuit as soon as the conditions have been fulfilled. So we get quite nice performance even though we're having to do the speculation. So we get quite a few nice advantages for this generative approach. We've got granular control over the type of data structures that each component, each system uses, and also the entity metadata itself. We can decide whether we want that pre-allocated as stack-oriented arrays, or whether we want to use dynamically sized heap memory. And this also means we have minimal branching. We can just linearly process all these procedures without too much effort. We get very simple output, and this makes us extremely useful for low resource and embedded devices. For example, without any changes the original physics ECS we defined earlier, you can compile with Ratel to an 8-bit 80 mega 328p RISC processor, for example, which is used in cars, and it comes out to about 5 kilobytes of program storage out of a roomy 32 kilobytes. And there's scope to reduce this further. So this makes it interesting for things like using embedded loops and things like that, and event systems with the ECS. So one of the more advanced features that Polymorph provides is system inlining or ownership. And this lets you inline the actual storage for the component into the system, and also links the lifetime of the components to the system row. So it's kind of like creating user-defined archetypes or clustered data. There's no indirections when the system iterates. So theoretically it's the maximum speed, although in reality it really depends on whether your code makes good use of pipelining or not, and so on, and how big your components are, etc. But one of the interesting things about this is actually that the lifetime of the components depends on each other. So you're coupling the lifetime to the system row. So for example, if we here define the move system with the prefix own for both pos and vel, we could just do one or the other, but here we're going to do both. This fully owned system means that both these components rely on each other, and if you remove one, the other's also removed. And likewise, you can't add one without the other. So here's an example of how this works in practice. If you try and create an entity with just pos when we've defined this own system, you get a compile time error saying that you can't instantiate the entity because pos needs vel to satisfy the owning system. And this also applies to add as well. So for example, you can't just add pos, you have to add pos and vel at the same time, because they essentially act as a single unit, and the storage for them relies on both of them being present. Another incredibly useful feature is events, and these get used quite a lot in polymers. They're expanded inline, and they allow you to run code when the state of an entity changes, for example, when you're adding or removing components, or when a system is being added or removed with different rows. And events also allow embedding further state changes and therefore further events if required. And these are checked at compile time to make sure that you don't have recursion, for example, even indirect recursion, like if there's an added event for a system that then adds another component that has its own event that tries to add something else that removes from a system and then adds it back again. That's all checked at compile time, and you will get compile time errors. And the nice thing about this is it's expanded ad hoc. So if you don't trigger these cycles, then it will just let you do it. But when you do trigger them, you'll get a compile time error. Though I would say that's not for the faint of heart, and probably best to stick to simple events for that reason. The other thing you can do is actually replace components during construction. And we're going to cover construction in a minute, but this basically means that you can create entities from templates, and some of the components can be just template oriented components that don't actually do anything on a live entity, and you might want to replace these with runtime components, and that means that they can trigger different systems and so on. So that's quite a nice feature. So here's a simple example of an event. We've got the gravity component we defined before, and we're going to invoke the onAdd event, which gets triggered when the component is added to an entity. So here we're just outputting a little message with echo, and one thing that I do a lot in the ECS is make sure that things are set up or provide default values in onAdd events, so it kind of makes things a bit easier. But we're also, in this example, going to perform a further state change of adding bounce if you add gravity. So these components can be sort of linked together. As soon as you add gravity, bounce gets added. And below we've got the onEntityChange event. So this gets triggered globally for any changes to entities, and you can use this for debugging or whatever state changes you need to monitor. So systems also provide quite a lot of different features, different blocks for different scenarios in order to do more advanced processing. So firstly, you can actually negate components. Systems could be, say, I want pos and vel, but in this example, don't add a row if gravity exists. So this can be quite useful for various design patterns if you need to have some kind of variant of a system or whatnot. You can also set up your own fields. So this extends the type for the system with your own fields and data. So this can be quite useful if you need system local data, for example, tracking something that you're processing or whatever. And you've got an init block that gets run the first time a system is executed, and there's a little flag you can reset if you need this to trigger again. You've got a start block that runs when the system begins processing, and the useful thing about this block is you can actually pause or unpause the system here, so you can actually control whether the system itself executes within this block. And then there's the complement finish block, which obviously runs when the system's finished. And here's an example of a system event which will run this code when the system has a new row added, and this is also incredibly useful for setting up data, for example, and there's also a complement removed event as well. You can also stream systems partially, so this will just run one row, and the next time the system is run, it will then run another row. This example has a fixed number of rows it will stream, but you can also just set the stream rate yourself at runtime if you need to. Or you can also stochastically select rows at random, so this is quite useful if you need to sample a random selections of rows. And like stream, it can be useful if you need to spread work over a number of executions. And here we just have the main system block. So this code is executed when the system runs. So in other words, assuming we've passed the start block and the system isn't paused or disabled, then this code gets run. But it doesn't actually use any of the entities or the components here. It just updates our field we've defined. So you can build systems that just do sort of generic processing. And in fact, you can also build systems that don't use any components at all and just integrate into the ordered pipeline that systems get run at. And another huge feature that I probably use more than anything else is dynamic construction. So here we've got the CL macro, which stands for component list, and we can build a template for an entity. So here we've got pos, vel, and gravity components, but this isn't a real entity, this is just a sequence. And we actually have to call construct to build it. But of course, the useful thing about this is we can just churn off loads of constructs. And in fact, you can pass a number to construct to build a set number of them. There's also another version of construct that takes multiple entities, so you can build a group of entities at a time, and there's actually events that let you tie these together, so you can provide a template to the construction, but I won't go into that here. You can check that in the manual if you need to. So you can see here, when we do build this construction, because we've added these previous events, we get a little echo for gravity added, and then the onEntity change event gets triggered because the onGravity add event adds the bounce component. But then finally the construct event is called, which lists the components that we've added, and the final result is displayed below, and we can see that this constructed entity uses all the systems that we've defined with the values we set up in the bouncy template construction list. And finally, here's a work in progress larger project that I'm building with ECS. So this is just a demo of the kind of stuff that you can do, how the performance looks when you start doing something a bit more complicated. So this is using the ECS for everything pretty much. There's no engine involved. Everything is just entities. All the little explosions are made with entities producing particles. All the world blocks are also entities. These little pickups are also entities, and so on. And other than that, I'm just using shaders to do all the lighting and stuff. So you can see the performance is quite nice here. We don't have to worry particularly about the ECS slowing us down. In fact, I rarely find that the ECS is a bottleneck in any situation, so that's pretty handy. You can see here when I'm building those bullets, that's actually a construction template that then builds another bullet that then fires out bullets. So it's quite flexible in how this is working. So that's it. Thanks for watching. I hope this was interesting for you, and if you've got any questions, feel free to ask. All right, cheers.